This video will provide background on the issue of multicollinearity. Multicollinearity is often described as the situation where multiple variables included in a regression analysis are highly correlated. If that's the case, by mathematical definition, the regression coefficients will retain predictive accuracy, but they often are described as unreliable or unstable. The reason why is the analytic solution is not able to distinguish the association between the outcome and each of the two individual variables. And this is because their correlation represents overlapping covariation with the outcome. While this is mathematically true, it can be hard to understand on an intuitive level. What it boils down to is regression coefficients that do not represent the true association because there is limited amount of variation in the outcome variable that both explanatory variables are competing to explain. This video will provide an example of how this occurs in simple terms to clarify the complex implications of multicollinearity. Suppose you had a room with 4 thermometers, one in each corner. Each thermometer provides a reading of the temperature in the room that is very close to the true temperature in the room, though each also has a slight inaccuracy. Maybe it's a difference in the thickness of the glass or the volume of mercury. Regardless, they are each imprecise to some small extent. Each thermometer, because of this, has a different value, though they all provide readings that are close to each other and close to the true temperature, as you would expect for any reliable and valid measure. Suppose now you select one thermometer to focus on, and you decide to use regression to predict the temperature of that outcome thermometer using the temperature of another predictor thermometer. This will mean a regression model with an intercept and slope coefficient relating the value of one thermometer to another. The question becomes, what is a true regression model solution? Feel free to pause the video for a second and think about it. All right, let's go ahead and write out the regression model here. We'll have temperature is equal to beta naught for the intercept, plus beta 1 times temperature 1, the predictor thermometer, plus random error, of course. The most accurate way to estimate the value of the outcome thermometer would be to simply look at the value of the predictor thermometer. And that's it. They won't be the exact same every time, but the difference would be attributable to random chance. So the best bet is to simply assume both thermometers have very close to the same value. In terms of the regression model, that would mean the intercept is 0 and the regression coefficient is 1, because we want to take the value of the predictor thermometer exactly as it is and do nothing to it. Now consider a collinear situation. Suppose now we have the same outcome thermometer, but instead of using just one thermometer as a predictor, we use all 3 of the other thermometers. And this means a regression model with an intercept, but now there are 3 regression coefficients corresponding to each of the 3 thermometers. The question becomes, what are the true values of the regression coefficients now? Maybe the result would be 0.33 for 1/3, essentially averaging the contributions of all 3 thermometers in predicting the outcome thermometer. Or maybe the results would highlight contributions of one thermometer that was slightly more reliable than the others. The answer to this question is not important. What really matters is that any one of these solutions would be wrong. We already know the true association for each thermometer with the outcome thermometer is a value of 1. This is what the problem of multicollinearity represents. By mathematical definition, the coefficients are derived to represent the most accurate predictions of the outcome. So in terms of making predictions, they are indeed mathematically unbiased. However, we have given the model too much information. It has to use all 3 thermometers to predict the outcome thermometer, even though any one would have been more than sufficient. So none of the individual regression coefficients will represent the true association. This is a problem of interpretation. If we try to interpret what the coefficients represent to draw a conclusion from the model, none of the coefficients lead to a correct interpretation. And there's no way they ever could lead to a correct interpretation, because at the point of analytic design, we have asked for something meaningless, an artifact of math with no relevance to the real world. This is a simplified example to try to make the problem explicit. In practice, multicollinearity can be subtle, which is why it's such a complex problem to address. Statistical tests for multicollinearity have been proposed, but I'm skeptical of how useful they are. If they are not significant, it does not necessarily mean multicollinearity is not present, but rather there was not sufficient evidence in this sample to detect it. Like all statistical tests, you should be cautious in accepting the null hypothesis of no multicollinearity in this case. This matters because as researchers, we all experience confirmation bias. So if I don't want to find evidence of multicollinearity and I don't see any evidence of it, well, I might just not ask too many questions or try that hard to find it. My advice is to make your research design very focused. Only include key variables that all represent unique information based on your understanding of the causal framework. No one study can answer every question. Measures could be multicollinear for different reasons. It could be because they represent aspects of the same underlying trait being measured. At the same time, if the sample size is limited or the analysis is very large, it's possible that the measures are collinear simply because of random chance. You only have so much data. So unless you go out of your way to ensure the primary data represent all possible combinations of traits included in the analysis, your sample may not be equipped to tell whether or not one trait was more relevant than another. The more you can focus on your hypothesized exposure and key confounders of the relationship between exposure and outcome, that can help you have a sample that can really answer your question in spite of problems of multicollinearity. This is especially relevant if you're working with a broad database. You don't need to include everybody in the final sample. A smaller, cleaner sample focused on just a few carefully chosen traits representing all combinations of predictor variables may provide a better answer to the research question than an overly broad investigation, which is relying on a convenient sample to try to do too much.